Welcome to a session on supercritical carbon dioxide. We all know that supercritical carbon dioxide is the carbon dioxide when its temperature is critical temperature, pressure critical pressure. And at that time, the volume will be very high and its properties are very different from that of a liquid, but at the same time it's not completely as a gas. Now before going to the topic, let's discuss the assignments and then go to the topic. So first, this is the assignment given in the previous class. State Cailletet and Mathias law of rectilinear diameters, and this is a principle we have behind the determination of critical volume by Amagat's method. Here Cailletet and Mathias law of rectilinear diameter states that mean of densities of any substance in the states of liquid and saturated vapor at the same temperature is a linear function of the temperature. Mean of densities of a substance in the state of liquid as well as in the gaseous state at the same temperature is a linear function of the temperature. The densities of saturated vapor in equilibrium with it, liquid and gas. This is the gaseous state. Okay, that is the saturated vapor which is in equilibrium with it is known as orthobaric densities. Now, law of rectilinear diameters can be expressed as dl plus dv by 2, which represents the mean of densities of liquid and vapor, which is equal to A plus B into T, where A and B are constants. dl and dv, they are the densities of liquid and vapor which are in equilibrium at a given temperature, are known as orthobaric densities. A and B are constant and T is the temperature in Kelvin scale. Now let's move on to the second question, which is given as assignment. What is the principle behind the Cagniard-de la Touze method for determination of critical temperature and pressure? In the last session, we have seen the experimental method to determine the critical temperature and pressure, and the principle behind that is the meniscus, which gives a distinction between liquid and gas phases, disappears at critical state. That is the meniscus between which separates the gas and the liquid. It disappears at the critical state. So that temperature and the corresponding pressure will give you Tc and Pc. So that is measured simultaneously. Now let's move on to today's topic, that is supercritical carbon dioxide. In this session, we'll be dealing with what do you mean by supercritical carbon dioxide and how is supercritical carbon dioxide prepared and some of its application. So first let's see what is supercritical carbon dioxide. Supercritical carbon dioxide, it is represented as carbon dioxide with a subscript before that is Sc, saying that it is carbon dioxide in supercritical state. Okay. Now, is a carbon dioxide which is a fluid state, it is in a fluid state, has a density of the liquid but behaves like a gas. It has got density of the liquid because after liquid it is just getting converted into gas. So, its density will be almost equal to that of the liquid, but it behaves like a gas and it is non-toxic, non-flammable and environmental friendly. So this type of carbon dioxide is known as supercritical carbon dioxide, and from this itself we can guess that this carbon dioxide exists at critical conditions. Okay. Now, when the temperature of carbon dioxide exceeds its critical temperature, what is that critical temperature? 31.1 degrees Celsius, and is subjected to a pressure of 7.4 megapascals, or you can say it as 73 atmospheres. It enters into a supercritical phase. The supercritical carbon dioxide is commonly used for solvent extraction process because of its high solubility, low toxicity and environmental friendly. But here there is one drawback, though we call it as environment friendly. If carbon dioxide escapes into environment, again carbon dioxide is responsible for the greenhouse effect. So that is, you cannot say it is 100% environmental friendly, but one thing is, it is not that toxic and you can remove carbon dioxide from the atmosphere either by planting more plants, or you can take out this carbon dioxide which is being expelled and we can recycle it. So methods are there, and it is not toxic as if we are using some other organic solvents, which is very much hazardous to the health of humans as well as for the environment. Now let us see the condition. See, this is any substance in the solid state. We have the closed packed arrangement. In liquid state, they move a little bit far away from each other. You can see there is some more space in between the molecules. And here we have the gaseous phase where we have the molecules are very far apart. Now, when it goes to the critical point, that is above the critical condition, you can say that this is the case shown for carbon dioxide. Now, that's why they have mentioned the pressure and temperature. This is 32 and here that it will be 31.1 degrees Celsius. Okay, once it enters into supercritical fluid, here it won't be having molecules as that far apart as in the gaseous state, but it will be a bit far apart than in the liquid state. So the densities will be, that is the density of the liquid in this region will be almost equal to that of that in the supercritical fluid. So density will be somewhat approximately equal to that of the liquid at the critical state, and we have the supercritical fluid which shows the properties of gas like easy diffusions and all those things. So this is what shows a diagram of how the molecules are packed in the supercritical fluid. Next, we will see how to prepare the supercritical carbon dioxide. The carbon dioxide gas is taken in a tank, and that tank, it should be able to withstand very high pressures. So it should be made with such a material which can withstand high pressures. It is then liquefied by cooling and applying high pressure. Okay. Now this liquefied carbon dioxide is pumped to a pressure above its critical pressure, that is 7.38 megapascals, or you can say it as 73 atmospheres. So the pressure will be slightly above the critical pressure, and then it is heated to a temperature about 31.1 degrees Celsius, and this is the critical temperature of carbon dioxide. Now what happens is, first we have been liquefying this carbon dioxide, and when it is pumping to another chamber where we have pressure greater than critical pressure and temperature around critical temperature, that is 31.1. At that temperature, carbon dioxide transforms to supercritical state, exhibiting properties between that of a liquid and a gas. It won't show the total properties of a gas, neither of the liquid. So it will be having a hybrid property of a liquid and a gas, and this type of carbon dioxide we call it as supercritical carbon dioxide. Now let us see the applications of supercritical carbon dioxide. First one is, it is an eco-friendly solvent. Because carbon dioxide, the supercritical carbon dioxide is cheap, it is not that costly, it is inert, it is readily available. Carbon dioxide is readily available, it is non-toxic, non-inflammable, capable of solubilizing lipophilic substances, and it is generally considered non-polluting in comparison to other toxic solvents, though it has got a greenhouse. It is a greenhouse gas. It causes greenhouse effect, but usually for solvents we usually consider mainly some of the organic solvents which are carcinogenic and it's not eco-friendly solvent. So, these vapors which they enter the atmosphere can pollute it, while carbon dioxide, if it escapes into the atmosphere, the only effect it causes is the greenhouse effect, and therefore this can be, we can minimize the greenhouse effect provided you trap this carbon dioxide and recycle it. So, you can avoid the excess of carbon dioxide getting accumulated in the atmosphere. Other thing is the recycling process where we are using it. And the other one is you can grow lots of green trees and all, which utilizes this carbon dioxide in photosynthesis. Okay. Now, its use enhances the quality of the products than conventional alternatives. That is, when we use an organic solvent and the product formed which has got some traces of organic solvents adhering to that, but in this case this carbon dioxide which is in the supercritical state, it can be converted into the vapor form from where it gets escaped from what we have been applying for. So, the removal of the solvent when we use supercritical carbon dioxide after the process is very easy, because what we have to do is depressurizing, which converts the carbon dioxide into the gaseous state. So, once it is in the gaseous state, it escapes from the substance where it has been extracted and you get the extracted material in the pure form rather than organic solvents. Okay. Now, this carbon dioxide then can be recycled. The only hazard is some of it may escape to the environment, which we can prevent it either by making the environment more greener. Next is supercritical solvent extraction. We know that for solvent extraction we generally apply hexane and many other organic solvents, and these solvents are all carcinogenic as well as they are poisonous to human beings as well as it causes environmental pollution. Now, if I use supercritical carbon dioxide as a solvent for extraction, because these have very low viscosities and high diffusivity. What does it mean? Its diffusion is very high means if you give a substance to be extracted and if I am using supercritical carbon dioxide, it diffuses within the substance and extracts whatever it is soluble in it, because it can diffuse into the material more fast than any other organic solvents, because it has got the properties of the gases. Now, just like liquid, it has got viscosities, but viscosity will be very low, and as a result it is very easy that it penetrates within the material to be extracted. Alternative solvents, they may be poisonous. What we are using, the alternative solvents, mostly they are organic solvents, they may be poisonous, and once removed some traces may remove in the what we have been extracting from it. It is not flammable, again that is another thing, and or an environmental hazard. They all have poisonous nature, they are flammable and causes environmental hazards. The extraction can be selective. You can selectively extract substance because density of supercritical carbon dioxide is being controlled. We can control the density of the medium, and the extracted material can be easily recovered by simply depressurizing it, which allows supercritical fluid to return into gaseous phase, leaving no solvent residues. That is very important. No solvent residues in the extracted material. That is what we have in organic solvents. Carbon dioxide is the most common supercritical solvent. Most common critical solvent used on a large scale for decaffeination of green coffee beans. Decaffeination means to remove caffeine from green coffee beans. So, this has got very high extractive power. It can penetrate into the coffee beans and extract most of the caffeine from it. Then another this thing is you can extract essential oils. Then pharmaceutical components from plants. All these things can be done using supercritical carbon dioxide and in a very large scale in industrial method. Okay. Next use is, it is used for dry cleaning, and dry cleaning we use petroleum solvents, and instead of that supercritical carbon dioxide can be used for dry cleaning solvent, but instead of any organic solvents. Now here there is some difficulty in some cases. Certain materials they dissolve in supercritical carbon dioxide. So such things can be avoided, and in other cases it can be used as a dry cleaning solvent. Again here no hazard of the remaining hazardous organic solvents or traces of hazard organic solvents in our dry clean clothes. Okay. Next is impregnation and dyeing. Supercritical carbon dioxide possesses low viscosity and high diffusivity. It diffuses very fast, and the viscosity, that is to pass it through, it is very low, and therefore it allows a rapid penetration of supercritical carbon dioxide into porous solid material. So, if you are having a porous solid material, supercritical carbon dioxide can diffuse into it because the viscosity is low and it has got a high diffusivity. It can go into the pores and extract or take out things from that. That is one thing. Another thing is, that is we explained in the extraction process. You can also deposit certain substances in the pores which is soluble in supercritical carbon dioxide. You dissolve it in supercritical carbon dioxide and pass it to it. It diffuses into the pores and you can deposit the substance in the pores, and you depressurize, the carbon dioxide comes out as the gas, and the substance we have dissolved in supercritical carbon dioxide and passed into the pores remains in the pores. Now such things are done to enhance the properties of certain solids. Okay. So that is what is said there. It is used to deposit substances which are soluble in it into porous solid structures to improve their properties. That is, you can improve their properties of that substance. Now that's an example over here. That is, supercritical carbon dioxide is used to deposit dyes onto a polyester on polyamide materials in certain pharmaceutical drugs components, all these into, that is, pharmaceutical drug components into some polymers, pesticides into wood and wood-like materials. Because we want to deposit dyes to polyester and polyamide materials is because if you use supercritical carbon dioxide, they penetrate into the fibers more effectively and the dyes are held there. And pharmaceutical drugs into certain polymers which should be applied into our system so that the polymers they react with our system, that won't be a hazardous one, okay, and the drug is being released. Then pesticides to wood and wood-like materials. We know that termites, they cause a large damage to wood and wood-like materials, and therefore to introduce pesticides into the pores of wood and wood-like materials, supercritical carbon dioxide is used so that you can prevent or you can have that termite resistant wood materials. Next is power generation. In power generation, we have seen that in Carnot cycle, it is an engine based on the temperatures of sink and source. Okay, that is eta is equal to temperature and the hot condition minus temperature in the cold condition divided by temperature in the hot condition. Greater the difference between the temperatures of these two. That is, one is a sink, the other one is a source. This is a source and this one will be sink. Greater the difference between these two, greater will be the efficiency. So, the temperature difference should be greater. So, efficiency of a Carnot cycle depends on the temperature difference between source and sink. Sink is that which I have shown it as TC, that is a cold condition. Source is where we get the heat energy and therefore, it is represented as temperature with a subscript H. It shows that it is hot. Okay, greater the difference and greater will be the efficiency. So, supercritical carbon dioxide works in having application in power generations as well as in refrigeration systems where it can provide the difference in temperature between the source and sink. Supercritical carbon dioxide can be considered as a working fluid which would have the advantage of lower critical pressure than water by taking into consideration of the issues with the corrosion. That is one point to be noted, because unlike water, carbon dioxide can have a slight acidic nature and therefore, it can cause corrosion. So, we will have to take consideration, we have to see that the metal is not getting corroded, and in that case you can use supercritical carbon dioxide as a working fluid, because carbon dioxide, it penetrates into very small voids in the material. Once it gets into it and it starts corroding, the material gets damaged. Okay. Next is in geothermal plants. Geothermal plants, they use the natural heat of earth to generate electricity. That is, usually water is pumped inside and at high temperature it gets converted, that is beneath the earth where we have the very high temperature of the magma, and there it gets converted into steam and it comes out and the steam turbines are turned to generate electricity. Now, here instead of water you can use supercritical carbon dioxide instead of water in geothermal working apparatus as a working fluid. Okay, that is what is in use in geothermal plants. Next is supercritical drying. Carbon dioxide can be used for fast and with lower energy consumption drying, because this is a method of removing the solvent without surface tension effects, because surface tension will be very low than any other organic solvents, and therefore, in this method we will have to remove the solvent as easy as possible, and since this does not have any surface tension, it comes out fast. The main advantage is in drying of biological samples and archaeological samples, in which the surface tension effect of the solvent can damage the structure, because once if it has got some surface tension, that is, if we are using something very delicate like some biological samples or archaeological samples, when the solvent is being pumped out from it by giving vacuum, what happens is the solvent tries to adhere to that, and as a result the structures, they get damaged when the solvent comes out because of its surface tension. Now, supercritical carbon dioxide, since it does not have any surface tension or appreciable surface tension, the removal of carbon dioxide cannot damage the surface or the structures from which it is being removed. So, for drying, it is better to use supercritical carbon dioxide, because in these cases the biological samples, they are so delicate, they should not get damaged. Then archaeological samples, you know that once it is damaged, it is gone forever, and therefore archaeological samples also you can use supercritical carbon dioxide for drying that, because surface tension, it drags on small structures within a solid, causing distortion, shrinkage when ordinary solvents are used. You can prevent that. That is, causing the destruction of the samples by distorting it or shrinking it, just like any other ordinary solvents that are used for drying. Now, to conclude, let us see once more what is supercritical carbon dioxide. Supercritical carbon dioxide, as I have told you, it is a fluid state carbon dioxide which has got a density of the liquid but behaves like a gas. It is non-toxic, non-flammable and environment friendly. And this usually occurs at around the temperature, it is the critical temperature of carbon dioxide is 31.1 degrees Celsius, and at a pressure of 73 atmospheres or 7.5 megapascals. Okay. And here I have shown the molecular arrangement. In solid state of carbon dioxide, it is closely packed. In liquid state, they are bit far apart. In gaseous state, it is very far apart. But when we come to the supercritical state, you can see that is something between the liquid and the gaseous state. It is not so close as in a liquid, but it is not as far as in a gaseous state. So, that is why the supercritical carbon dioxide has got certain varying properties rather than a pure liquid or a pure gas. This is here we have been seeing the applications of supercritical carbon dioxide, and researchers are going on to explore more supercritical fluids. Okay. And the preparation is, we are taking carbon dioxide in a tank, we will first, which can withstand very high pressure, we will liquefy it and then pump it into another chamber where the pressure is high while the temperature is around 31.1 degree Celsius. Pressure will be a bit higher than the critical pressure, that is 73 atmospheres or 7.38 megapascals. And then we have been seeing the applications. We know that it is an eco-friendly solvent. It is a non-toxic, it is cheap, it is easily available, all those things are there. It is somewhat inert also. And the thing is, the removal of solvent is very easy, just reduce the pressure, the supercritical carbon dioxide evaporates out of the substance. Then it can be used as a critical solvent, supercritical solvent extraction, because it has got very low viscosity and it diffuses highly into the material. So, for extraction it is quite easy, and we know that it is used for decaffeination of green beans, coffee beans, then extraction of essential oil from number of, it can be either from flowers, spices, anything else, and to extract pharmaceutical components from the plants. It can be used for dry cleaning because it is a very good solvent. At the same time, it is not hazardous as the organic solvents we use in dry cleaning, and it will not leave any residues in the dry cleaned material. Then impregnation and dyeing we have been seeing, that is, if you can deposit something within the pores to enhance the properties, and so that you can use supercritical carbon dioxide, that is depositing dyes into polyester and polyamide materials, then certain pharmaceutical drugs into certain polymers, pesticides into wood and wood-like material to avoid the attack of the termites. Then for power generation, it is usually here for geothermal processes we use water, and instead of water, if you use supercritical carbon dioxide, you can have a lower critical pressure than that of water, and therefore the temperature difference, you can have a greater temperature difference between the source and the sink, thereby enhance the efficiency. Okay. In geothermal plants also you can use supercritical carbon dioxide because it can have a better working fluid than water, which is at present considered as a working fluid. And again for supercritical drying, here it has got very low energy to remove the solvent from that, and therefore removing the solvent again, because it has got low surface tension, it does not damage the substance from which it is being removed, and therefore especially for biological samples and archaeological samples, they do not get damaged, because if some other solvents are used, because of their surface tension, some of the material will be pulled up along with the solvent, or you can say that it causes some distortion in the substance from which it is being extracted, and as well as it causes shrinkage too. These can be avoided if supercritical carbon dioxide is used. So, that is all we have been seeing about supercritical carbon dioxide in this session. So, with this I conclude. Thank you.